do that. Okay, so the video is now running. I guess that's okay. Sharing with the YouTube community what your due dates are doesn't really matter. So are there any questions regarding due dates? I'm not going to change them or anything, but did everyone that's paying attention get that? What? Yeah, okay, yeah, I got some yeses. Thank you. Good. What is the message I'm conveying?
Pay attention to due dates.
Pay attention to due dates and prioritize your time.
More specifically on that, you got a lot of stuff coming due in the next 10 days. That's what I'm trying to convey. And as a strategy for doing that, because I know this is not your only class, take a look at them. By all means, do the easiest stuff first and hand it in, which is opposite of how my mom taught me to take tests. But I've had enough life experience to say for stuff like this, or things where nothing is mission critical in the bigger sense of the term, it's usually better to do the easy stuff first and get it out of the way, because that whatever time you have left then gets devoted to the hard stuff. If you start with the hard stuff first and get stuck, which does happen even to real people, then you lose out on any reward that you would get for getting the easy stuff. You got a lot of stuff due in the next 10 days. Let's now return to the lesson for today, which is not 0. It is 13. I'll take a link to the content, and this is what the content link should look like. And I'll be working on the one called lesson 14 DEV. The ones with the O's in it are old versions. They're there because I haven't removed them yet, but you're not going to want to necessarily work on them. Let me bring up my Jupyter Lab instance, and that is lesson 14. Let me close it and reopen it. All right. So is everybody ready for the hour and a half of confusion? Now you can type a yes, anybody. Thank you, Marlene. Okay, great. And what's funny about me using the word confusion is later on, Farhang's going to teach you, not today, but he's going to teach you something about a confusion matrix. So confusion, believe it or not, is a multidimensional process. And we have a whole matrix devoted to it. So the topic for today, I've entitled it, pardon?
A quick question, please. How about the quizzes? We're not going to have them in the next 10 days?
I haven't, the only quiz I have available, and I haven't posted it, is a quiz on classes. Okay. So no, I don't intend to activate a quiz in the next 10 days. You just have those things due.
Okay, thank you.
But thanks for asking me, because one of these days I got to get the other 22 quizzes posted. So yeah, no, it's okay to keep reminding me. We won't get 22 quizzes this semester, but someday, years from now, they will. So in the next 10 days, a couple of labs and homework assignments are the things that are coming due. So the title for today's lesson is called Probability Estimation Modeling. And it's got 3 words in it. Probability, so that is one dimension of confusion. Estimation, which is a fancy word for guessing, a second dimension of confusion. And modeling, the biggest dimension of confusion, because depending on what we think a model is, that adds to the confusion. So we got a 3D confusion matrix right there. Just kidding. What probability estimation modeling is things we've looked at last time, which was nobody was uncomfortable with passing a blue curve through red dots. So when I'm presenting it, I use blue curves and red dots. The curves represent what?
The model.
The model. Oh. You're correct, the model. And the red dots represented?
The data points, sample.
Yeah, observations, sample, data points. Excellent. The colors didn't really matter, but the marker versus line is the convention that we are trying to convey to you all. So nobody had a problem with that. And then we introduced the idea of just a key on a calculator. That special function can be a polynomial, it could be the natural logarithm, or it could be something that we call probability distribution functions. So 3 different names for the same thing, a flipping key on a calculator. So now we're going to extend those fundamental ideas and make a few additional stipulations. So when we're using as the data model a special function that happens to be a probability distribution, and one of those axes happens to be the estimate of probability, and the other axis could be the value of the variable, that's all probability estimation modeling is aimed at. As we go through this, try to keep in mind that what we're trying to do is put a blue curve through red points and then make inferences based on interrogating things about the blue curve. The reason being is the blue curve is our best guess of what the underlying population does. And so we're asking the curve to tell us, what would the population do if we made one more observation? And so the objectives for today are going to revisit fitting a function again, just to keep that refreshed. And then we're going to look at a few special cases, plotting position formulas. I'm just going to use Weibull in the presentation. You'll get more exposure to that in your laboratory. A normal distribution, a gamma distribution, an extreme value distribution, and the Pearson type 3 is a special type of gamma distribution. The computational thinking concepts that we're focusing on in these objectives are decomposition. So our main thing we're doing is we're asserting that the data are drawn from some process that's functionally explainable, and actually we're making a further assertion that that function is a probability distribution. We're invoking principles of abstraction, where we're going to represent the behavior of that sample with the function, and it's all going to lead towards an algorithm design, in that we're going to use the function after we have fitted it to our red dots to predict new values of observations. That's literally all that's going on in data modeling. So let's refresh what we did last time. Last time, as you recall, we had the time speed example. I'm going to repeat that, but I'm going to go faster because there's only a subtle change. So we would prepare our data. We would pick a data model type. In this case, I'm going to use a polynomial. Actually, can go up to order 3, allow a qubit. We use some plotting tool to plot the observed data. In my case, I'm using red, and our model in blue. And then we're going to adjust the knobs on the model, the knobs on the microphone, to make the chewing sounds and the drinking sounds even better for our YouTube video, where we're going to make the real cache. We adjust those knobs to get the blue model to go through the red dots as best we can. So anything surprising there? That should be like deja vu from Tuesday.
Hey, this looks really familiar.
Okay, good. So you are having deja vu. Excellent. That's the plan. So here's the time speed example, and the only change I've made is I've put a polynomial that can take up to a cubic. So we have B0, B1, B2, and B3 are our parameters, and then X is some value. In this example, it's going to be time, and X is cubed multiplied by B3, and then added to X squared multiplied by B2, and then added to X times B1, and then added to B0. So very, very simple polynomial function that goes by the very clever name of polynomial. I was going to put starving parrot, but I'm not sure anyone would get the pun, so we'll stick with polynomial. And then we have our plotting function again. There's no change there. The only thing that's in here that's possibly different is the legend is supplied as a list of two string values, one named series 1 and series 2. And a better implementation of the make2plot function would be to add to the positional argument list two more strings and then drop them into these locations to plot the legend. But we're going to do it hardwired as it is right now. So let's go ahead and load in our data model, and then we'll go through our fitting process. And if we do that, we get this. I haven't run it yet. We get this curve. But let's see what we remember from our math class, which I hope you've had. If we take a polynomial and we really starve the parrot, so it doesn't get, it has a 0 value for intercept, the linear component is 0, the quadratic component is 0, and the cubic component is 0. And we plot that. What do you think the blue line would look like when I run this particular fitting process?
The blue line at y equals 0.
Yeah, it would be a horizontal line passing through the value of y equals 0. So let's go ahead and confirm that. Now, is that blue line at all a useful model of these observations?
No.
Yeah, that'd be a no. Okay, good answer. Is there a physical condition? Is there, I just looked at the chat box. Is there a physical condition where that blue line would be an effective model of something real?
Yeah.
Yeah, it would be the case where we're looking at Newtonian mechanics, the object's at rest, and there are no unbalanced forces on it. So kind of like how any of us are when we get into a recliner chair on a Sunday afternoon after a hard day of playing out in the backyard or whatever you do for fun. You basically are just a blob. Yeah, that models the speed of my mechanic while working on a car. Excellent. So you got, good, you've got the idea. Well, let's go ahead and try to improve our fit. And we're going to do this manually. And I left notes to myself if I want to get fancy. Let's go ahead and crank up the linear component. And that's still not good. Let's try a value of, say, 3. So 6 times 3 is, yeah, that's, and we could play that for a while. But at this point, we should visually be able to detect there seems to be curvature in our red markers. So we can invoke curvature by bringing to life the quadratic component. And, oh, that's an improvement. Let's drop the linear component a bit. And so we're close. And let me go ahead and activate the cubic. I forget what the value is. Actually, I left notes. There I go. For when you go and do client management long after you graduate, if you're doing demonstrations like this, always leave notes to yourself, because when you're in a public presentation, it's quite possible for your brain to lock up in ways you can't imagine. And let me put a little bit of cubic component in it, see what happens. I know I can get a better fit than what I have here. Let's see, drop the slope. And if I wasn't stupid, I would have 2. And I don't want to go through a long process. Ditch that slope. Okay, so trial and error would eventually work. Let's say we're happy with that, okay? So now we have intercept of 0, linear component of 1.6, quadratic of 0.9, cubic component of 0.02. That should crank it up just a bit. Let's say we're happy with that. So now we have a blue model of the red dots, and compared to our, oh, I like Caden's answer, so I'm going to try his. So here we go, Caden. Oh, that's a beauty. Excellent. Thank you. Good advice. So we will stop there. There's our model. Now, compared to our first one, where everything was set to 0 and we had the horizontal line, would you say this is a superior model of these data?
Yeah.
Yeah, that'd be a yes. If you chose any answer other than yes, you might want to practice saying, would you like fries with that, sir? Because you're clearly not paying attention. So that's a better model. So what we have done is we have fit our blue line through our red dots. And the purpose of doing that at some point is we want to use that model to answer questions about the underlying process. So let's say we're interested in how fast things are at a speed at a time of 4.5 seconds. We create this variable named time to go, and then we just print the estimate and we put in our polynomial with our parameters and then our new time value, and we get, says at 4.5 seconds, our estimate of speed is 25.5 units. And let's see if that makes sense. It's going up to this part of the blue line and it's reading back, roughly between 20 and 30, so 25. And that's interpolation. And in general, you could probably get as good an estimate in this particular instance by simply drawing a straight line between 4 and 5, and then either graphically or applying the principles of linear interpolation directly. But what we can't do with linear interpolation, but we can do, because we now have a model of the process, is we can go beyond the range of observation. That's called extrapolation. Generally, it is discouraged in many engineering contexts, and you will get that beaten into your head in other classes. However, extrapolation is the whole point of modeling. So now we're going to go to 6.5 seconds. What's your best estimate before I run this of what the speed will be at 6.5 seconds?
Probably around 50 or 51.
Yeah.
Okay, how'd you come about that? That's good observation.
I just ran the code.
Okay, well, that wasn't what I was after. But well, if we look at 6.5, we're off to the right of the chart, and our blue line at 6 is going to be a little bit over 40. So if we go to 6.5, we expect at least to be bigger than 40, unless it just fell off a cliff. So now we'll run it at 6.5, and we're at 53. And in the olden days, when we did this with cubic splines, which is something you can go look up on the internet, it's a quaint little device that you'll be lucky. You'll have to find your older professors, my age and older, that probably have a cubic spline or two sitting in their top desk drawer, and they haven't used it in 25 years. But it would give us the ability to graphically extrapolate at least a little bit. All right, any questions before we proceed? So,
No.
So what we're after here, what I'll reiterate is we have some data which are represented by the red markers, and we've picked some model out of the universe. We've adjusted the parameters of that model until the model explains our red data. In this case, and by meaning explain, fits it. And then we use the model for asking questions about the underlying process. So this was a nice physics-based thing, so everybody's brain can wrap around it easy. Let's go ahead and take that brain and put it in a blender and turn it into mush. We're going to go to probability estimation modeling. Same idea, but a few things change. So probability estimation modeling is using probability distributions or population data models to model or explain behavior in observed sample data values. So the distribution's a model. We have a sample. We're going to use that sample to adjust the shape of that model to fit the sample, and we are going to stipulate that we think the sample came from this particular population. Therefore, by fitting the model, we now can make assertions about how things are going to behave if we were to take another sample. So once that particular distribution is selected, then we can look at the concept of risk and explore it for events of varying magnitudes. And in this case, events, think of that as a possible value of the next observation. We've already introduced two important extremes in engineering, rare things, such as floods, nuclear power plants blowing up, etc., or common things, routine discharges, traffic accidents, network failure on a due date. I mean, that's the closest probability to one of anything that you guys will encounter, at least for the rest of this semester. Just told you have a bunch of stuff due in 10 days. 9.99 days from now, what's going to happen to your network? It'll fail, especially if you haven't uploaded your stuff yet. Okay, so the probability distribution is just a model of data. Yellowstone erupts. Yeah, that's an example of hopefully, if you happen to be in northern New Mexico or Wyoming, you hope it's a rare event. The probability distribution is just a model of the data. You can think of it as it's a replacement for the polynomial function in our previous example. So like a trend line for deterministic behavior, different distributions have different shapes. They have different domains and can explain certain types of observations better than others. So the fact that they have different shapes is what we leverage when we do this for real. Some of the useful distributions that are used in a lot of aspects of engineering, not just civil engineering, not just water engineering, although I apologize, those are the examples you're going to see today, are normal distributions and log normal, and then the one that we'll eventually name after Abby, the Abby normal distribution, the gamma distribution, the Weibull distribution, and extreme value distribution. There's several of them. The one we're going to look at today is called the Gumball distribution. So you can think of it as a gumball machine. That's probably something else that's very quaint to you. Beta distribution, there's a whole bunch more. We're going to look at examples of the first three. Weibull distribution is a special case of gamma, and the gamma distribution is built on top of beta distributions. An extreme value distribution with a whole bunch of calculus is a special case of gamma. Okay, there's a whole lot more. These are just a few. They occur frequently in many disciplines, primarily because these few work reasonably well for most instances of interest, and they are comparatively easy to explain. As long as there's statisticians, there's going to be weird distributions, because the only thing a distribution really has to have is it has to be defined on the domain minus infinity to infinity, and its density, which is a property of the distribution, has to integrate to 1 on that domain. Other than that, they can have all sorts of goofy ass shapes. So that emits a whole lot of things. I believe a countably infinite number, but this is not a math class. These probability distributions or models are usefully expressed as density functions and or cumulative distribution functions. And we'll make a picture of both of the normal, but mostly what's useful, what we're discussing today, will be the cumulative distribution function. And I'll try to suggest what that distribution function is conveying in a second. So let's go visit our friend, the normal distribution. So we have the normal density function and the normal distribution function, and we saw the arithmetic for these last time. 1 over the square root of 2 pi sigma squared e to the x minus mu quantity squared over sigma for the density, and the integral of that for the distribution function. So here's our density function, and I've rewritten this slightly from Tuesdays, and then I put the positional argument in the form of parameters and then the variable. And hopefully I've done that throughout this rewriting of this particular lesson. So our density function has two parameters. One parameter is named mu, because it's the sound that my cats make. And the other parameter is named sigma, which is also the cat sound it makes right before it scratches your eye out. And then the variable is x. So we've seen these already, so let me go ahead and load them. And why did I import the math function? Excuse me, the math library.
Because you need it for exponent and integral.
I need it for exponents, I need it for square roots, and I need it for pi. And I need it for the error function. So I need it for a lot. That's why I imported it. And now we will build our standard normal distribution. And I've plotted it. So the red, in this case, these are both models. The red upside down triangles represent the density, the normal density function. So to obtain a cumulative value of the density function, we integrate from minus infinity to the right. So for example, the integral of the red triangles from minus infinity to -5, for all practical purposes, has 0 area under it. And so the blue value at -5 is associated with 0. If we go to the center of the distribution, that represents half of the total thing. So the integral of half of the total thing of something that's supposed to integrate to 1 is half. And if we look up here, we are indeed at the 50th percentile. So the integral from minus infinity to 0 of the red thing is a half. The integral from minus infinity to 2.5 of the red thing is pretty high, like 0.9 something. And if we go from minus infinity to infinity, the integral of the red thing is
1.
correct, 1. Even the silent one for the muted person that said 1 to their camera. You were correct, muted person. And we can also look at the complements of that. The integral of the red thing from 0 to positive infinity, which represents the right half, is going to be the difference of 1 minus a half, which is a half. And so we can look at either the left or right side. So I'm going to pause for a minute and let that sink in. Before we proceed, without necessarily understanding the intricacies of the arithmetic involved, does the explanation make sense? The
Yes.
the blue curve represents the integral of the red thing moving from the left to the right over the different values of the random variable. So now let's depart from that picture, but keep it close to your short-term memory. We use these ideas to model data, generally to answer a fairly simple question. The question's simple to ask, which is, what is the probability that we will observe a value of the random variable less than or equal to some sentinel value? Let's go back to our other picture. So in this one, the value of the random variable is on the left-right axis, also known as the abscissa, and the associated cumulative probability is located on the up-down axis, also known, actually also known as that's the abscissa, the left-right's the ordinate. See why you don't want to use those fancy-ass words? Nobody can keep track of them. Left-right is our random variable, up-down is our accumulated probability. Now, visualize taking this figure and rotating it. Let's see if I get the rotation correct. rotating it to the left 90 degrees, and then flipping that so that your up-down axis is now the value of the random variable ranging from minus something all the way up to plus something. And the left-right axis is now the quantile value going from 0 to 1. So when we make that flip, we come up with something called an exceedance probability diagram. And so here is an example of an exceedance probability diagram. The horizontal axis is in probability units. The vertical axis in this case is in random variable values. And I have intentionally removed the axis labels in the title from this figure. This is a flood frequency curve for somewhere. And when presented in this fashion, the blue line represents our integral. So the blue line here and the blue line here are playing the same role. And for any value of the random variable, so let's say we go to this value, 10,000, 20, 30, 40, 50. It's a logarithmic scale. If we go to random variable value of 50,000, and go all the way over to our model of the underlying data, and then come down, the value of 50,000 corresponds to a probability axis value of 0.1, or a 10% chance. But then we have to decide whether we're interested in the behavior of the random value in smaller or the behavior of the random value in larger. So if we're interested in the probability of observing a value of 50,000 or bigger, we're looking above this line, which consequently is going to mean we're looking to the right of the intersect, and that would be called an exceedance probability. And if we're looking to the left, we have non-exceedance. And in the way these curves are usually presented, what the curve is showing is the non-exceedance probability on the horizontal axis. So the chance of observing a value of 50,000 or smaller, according to this data model, is 10%. Consequently, the chance of observing a value larger than 50,000 is going to be 100% minus the 10%. I get that backwards again. 50,000 or less is going to be 1 minus the 10%. 50,000 or more is going to be the 10%. I said that all backwards. My brain was locked up. So the plot is exceedance probabilities. If we want the non-exceedance, we subtract the exceedance probability from 1. And that's because those are two mutually exclusive conditions. And recall when we introduced probability a couple of lessons ago, that if all the outcomes are articulated and their probabilities are known, they have to add up to
1.
1. So this blue function is often called the quantile function, and a notation for it is capital F of cap X, where capital F represents the attained probability, usually exceedance probability, but not always, and X is a specific value of the random variable that we are going to express that probability relative to. So from that diagram, the random variable value of 50,000 is indicated by the horizontal magenta line. No, that's not the meaning of non-exceedance. It's not happen or not happen. It's magnitude lesser or greater. So non-exceedance means it represents the probability that you will observe that magnitude or smaller, or alternatively, you won't observe anything larger than that particular magnitude. So the random value in the horizontal magenta line is 50,000, and the blue curve is our data model, one of the distributions, and the accumulated probability is 0.1 or 10% chance, but then we have to stipulate whether we're interested in the less than or greater than. So in the figure shown that is slowly disappearing from view, the probability that we would observe a value of x smaller than or equal to 50,000 is 1 minus 0.1 or 90%. So it's 90% likely that if we go out to this function, whatever it's representing, these are stream flows, but it could be anything that's representable, and look at it right now, we have a 90% chance that we will measure a value smaller than 50,000 or upwards to 50,000. The chance we see something bigger than 50,000 in that instance is only 10%. And generally in words, we would take that very simple idea and use every word in the dictionary, which makes report writing easy because they get plenty long, plenty fast. The probability of observing a value less than or equal to 50,000 is 90%. The other side of the vertical line is the exceedance probability, which is actually what's plotted on the left-right axis. And the way we would write that is the probability of observing the random variable greater than 50,000 is 0.1 or 10%. In other words, you would state that the probability of observing a value equal to or greater than 50,000 is 10%. In risk analysis, the sense, exceedance or non-exceedance, it gets really easily confused in your head. So whenever you can, make a plot. That's probably the best advice I'll ever give you. That and wear sunscreen when you go out in the sun. Make a plot, because the plotting activity itself will help you clarify in your own mind whether you're looking at greater than exceedance or less than non-exceedance. Another way to look at the situation is simply realize that the blue curve itself is just the quantile function, f cap x, with cap x plotted on the vertical axis and f of cap x plotted on the horizontal axis. Now let's put these ideas into use. So we're now going to start doing some simulation and making blue curves go through red dots. Everybody ready?
Yep.
Okay, I'll wait a little bit so that everybody's springs can reset, and then we will get started. Okay, I got a ready from Julissa and from Sean, so I will go forward. So we're gonna do some simulation. So let's first we're gonna import our NumPy module, and we're gonna create an empty list that goes by the name of population. The name is just a name, but I chose population for a reason. That'll probably make sense shortly. And then what we're going to put into our population list is some things. And based on that for statement, how many things are going to go, how many times is that loop going to be executed?
100.
25.
100 times. It's going to start at 0. It's going to end at 100. So they're actually going to end up with 101 things. And what we're going to do is for each value of the loop counter, we're going to put that value into our variable named populate, our list named population. And then we're going to sample 25 things from that list. So I can run it this way, or do you want me to split it out and we can go look at the contents of population?
I think I'm in the contents of population.
Okay, let's go ahead and split it. And it didn't work the way I wanted to because it's a computer and its purpose in life is to make me want to quit. So we've just filled this object named population, and now I'm going to simply type the word population, run the cell, and it should return the contents of population. Sure enough, it starts at 0 and it ends at 100. So there's 101 items in population. What can you say if you were to verbally describe population? I don't mean describe like the describe function. Tell me what population is.
Population is the entire set of data, like where you pull your samples from.
Yeah, it's a list of integers from 0 to 100, inclusive. So if I'm not going to attempt to plot it. If we histogrammed it, it would be a weird looking histogram. So that's what's in population. Let me go ahead and suppress the output because it's going to get in the way. Now we'll sample from population. In fact, let's take a look at the contents of sample. What do you think will be in sample?
25 random digits between 0 and 101.
25 random things between 0 and 100. Yeah, you're correct. So let's go see if that's the case. The first thing was a 97, a 19, a 76, a 67, 68, a 17, another 76, 16, 44, 98, 95, 42, 81, 54. I'm hoping there's another duplicate. Well, we got at least two 16s. No, two 76s. Anyway, there's a few duplicates, two 7s. So there are some duplicates. That's our sample. So we've gone to this population. We grabbed a number out of it. We wrote the number down and we threw it back in the population bucket, shook it, did that again, wrote the number down, threw the number back, shook it, pulled the number out, wrote the number down, threw it back, shook it, did that 25 times. So now our sample has just 25 things in it. Let's get some statistics from that sample. Since the sample is a NumPy array by construction, we have the mean method available to us and the standard deviation method available to us. And recall when we introduced descriptive statistics that sample variance is simply the square of the sample standard deviation. And I'm choosing to do this to be consistent with your future probability and statistics classes. So we can get the mean and we can get the variance. Any speculation on what the value of the mean would be just by looking at those numbers?
Maybe like mid 40s.
Okay, so we have a guess of mid 40s. Let's see how close you are. 52, not bad. I'm not even going to ask variance because I can't possibly do that in my head. And so, how did you come up with the 40s? I mean, that was a good guess. And
Well, I know the average of 100 should be 50, and I was just glancing at it. It looked like there were more small numbers, but I guess my intuition was wrong. There were more big numbers.
okay, but that was very good algorithmic thinking. That's correct. That is exactly what we expect. What you did in essence was, because you knew the population, you know all the information. You're God, and as God, you know that the mean of the population is 50. As a demigod, you know that you've taken 25 things out, and the high value and the lower value are pretty close to the endpoints of your God population. And then you speculated that there's more smaller numbers than bigger ones, so that you guessed a high 40s value. And that's correct. Keep that in mind during the lab because you're going to get to play God again. They do get to play God today, don't they? I'll look in the chat box. Farang, they do get to play God again today, right?
Yes, to some level.
Okay, good. It's always good to play God. So never turn down a chance to play God on your computer because they usually can't hurt you back. All right, so now we have our sample mean and our sample variance, which are just descriptive statistics of our sample array. We could even get fancy and do what's our favorite method? I hope this actually works. Oh, that actually might be a pandas method. Yeah, that's a pandas method. My bad. Never mind. Nothing to see here. Move on. Okay. So we'll sort the sample in place. So all I'm going to do is take these numbers and rearrange them from small to big. That's what the sorting method does. And then I'm going to create a relative frequency approximation to probability. So what I'm going to do is say that the chance of seeing any of these 25 things in the sample is the same. Once I have the sample, we're declaring it's as if it's a new population. So the chance of seeing any one of these particular numbers in any draw is 1 divided by the total number of numbers there, and we're going to accumulate them. That's a Weibull plotting position. You'll get more instruction on that in the laboratory today. But for the time being, all we're doing is we've sorted the contents, and now we are counting their positions. Notice at no point do we need to know the value of the item in the sample. We just need to know how many things there are. So we're counting their positions, and we're creating a list called Weibull PP, Weibull plotting position. And what it represents is the empirical, or the data derived, the empirical probability, cumulative probability function. So it's an empirical expression of what we would think that blue curve might look like. There are a few different plotting position formulas that in practice you will choose depending on what your underlying data model is going to be. So before I run that, is that fairly clear? Again, not necessarily understanding the deep background of the theory, but all we're doing is sorting the sample from small to big, and we're counting the number of things in this sample, and we're ranking them. We're assigning the smallest thing the rank of 1, the biggest thing, see if I'm doing this, the rank of 25, and then we're dividing by the total number of things. So the smallest thing has a value of 1 over 25, the biggest thing has a value of 25 over 25, and then we're jacking with the denominator a little bit by shifting it by numerical value of 1. So this first one is 1 over 26, the last one is 25 over 26, and then they're spaced accordingly in between. So move on. I will take the awkward silence as a yes. We completely understand it, and I can do this on a pop quiz that's going to happen in 10 minutes. That got your attention. No pop quiz.
I had one question.
Good.
So you shifted to get a percentage, right?
So I shifted this to +1. Yeah, it's actually a pretty deep question, and I'll do my best to answer it fast. Because it's a sample, the chance that we have defined the whole universe is low. And so by shifting it to 1, we are admitting that there's possibly values smaller than the smallest and possibly values larger than the largest.
So it's like leaving a room for error.
Leaving room for additional observations.
Okay, thank you.
So let me go ahead and run the sort, and then our make a 2 plot function is listed here. Nothing surprising there. I've labeled my horizontal axis, left, right, and my up, down axis in a title. And I'm not going to mess with the series 1 and 2. I have put some effort into trying to keep the markers as observations and the lines as our model. So we run that, and there's our blue model. And our first observation is, what a piece of crap plot, right? That blue line is in no way useful to tell us about the behavior of the red markers. Would you agree? Actually, of course you'll agree because I'm talking, but you get that?
Yes.
Yeah, our goal is to try to make the blue line go through the red markers, and we have failed miserably in this. Actually, not as miserably as we could, because at least they're on the same plot. But we've pretty much failed. But if you recall, when we made the blue line, we we never used anything from the actual sample data. All we did was sort it and rank it and assign a value of 0 to 1 depending on the data position. So now let's turn some knobs on our model. We're going to use our normal distribution because that's the only thing we know how to do right now. And let's start fitting things. So our value for mu, we'll take that as the sample mean, which we've already computed from the red markers. And our value from sigma we'll take as the square root of the sample variance, which we have also already computed from the red markers. And then we will construct our new blue line model. And we'll take advantage of some features we have. Because it's a model, we're not constrained to just 25 markers. We can use more. So we'll start at a value of 0. We'll end at a value of 100. We'll break that into 100 parts, and then we will step through parts equal length. So what we're going to have is 0 to 100 is probably going to be in steps of 1. And we will append our x value to get the horizontal, the left-right axis. We will create a y value based on the normal distribution of now our new model with mu and sigma and our arbitrary x location. We'll append that to the YCDF object. We'll build a title. And the only reason I did this is the title's starting to get long, hard to write now. And the title is going to be normal distribution data model. And we'll report the sample mean. And then we'll report the sample variance right in the title. And that'll be handy for looking at results. And then we'll plot the 2 lines. So let me go ahead and do that. Make the title. And now we make our plot. And now comment on the blue line. Is that an improved fit over the last one?
For sure.
Actually, I didn't ask the question exactly right. Is that an improved model of our data over the last one? And
I think
the answer is yes, for sure. That's far more useful. Although the blue line doesn't exactly go through the red markers, but it sure does a whole lot better than the flat line that we had before. And so that if we were to stop here and say, well, that's good enough. It's a engineering class. I'm a engineering foundational student, and they're all kind of on the same plot. And I've got more important things to do than learn this statistics stuff. I'm going to stop here. And if I were to ask you, what is the chance of observing a value in a sample of 80 or smaller?
$80 or smaller, it's pretty close to 80%.
80 or smaller is, yeah, a bit more than 80%, or a bit more than 0.8. 80 or larger, a bit less than 20%, or a bit less than 0.2. And if I were to suppress the red markers, you can still answer questions like that as long as you have the blue line. Now for grins, since we have the population, we can go back and do this from a God perspective. I'm just going to repeat the plot, except instead of using the sample mean, I'm going to use the population mean, population variance. So everything else is the same, and we're changing the title. So if I do it with population mean and population variance, the blue line at first glance looks almost the same, but keep your eyes in this corner and down in this corner, and I think I can get the two on the same. Now they're slightly different, which is to be expected, that the population mean and the sample would be different, but they're awful close. And so that is a fairly important observation. Let's comment on that. Just some observations up to this point. Our population happens to be something called a uniformly distributed collection. By random sampling and keeping our sample size small, our sample distribution appears to be approximately normal. Now, the population is not a normal distribution. It's uniform. And our sample is not normal distribution, it's uniform. But in small sampling, a normal distribution is often a pretty good guess. And in this case, it's a pretty good guess. If we had no other information about the population, if we didn't know that we actually created it from the integers 0 to 100 inclusive, the normal distribution model, because we wouldn't have this second plot here, would be a usable data model for a lot of things. Obviously, depending on the severity of failure. So let me repeat that because we have, yeah, we're good on time. Let's see, wait, 10 to, yeah, we're good on time. Let's reduce our sample size quite a bit. So we did a sample of 25. Oh, somebody pick a number between 5 and 7.
6.
6. Okay, so we'll do a sample size of 6. Okay, so that's a relatively small sample. So now let's look at our sample of 6. The smallest number is 41. So I expect this is going to be quite a bit different. So there was our initial model. And now let's do the fitted one. So there's our attempt to put our data model through our 6 observations. And actually, that's not horrible. Let's see what happens when we pass the population model through the same data. If we actually pass the actual population model, that is a pretty horrible model. So the normal distribution, oftentimes in cases where we have no other information about the underlying process, returns a usable model. In this case, it would definitely be usable in the range where we have actual observations, and it starts to become absolutely useless if we were to extrapolate to smaller than our smallest value and extrapolate to larger than our largest value. And that's pretty typical of probability estimation modeling. So now I'm about to move on and do it with some real data, but let me stop here and see if everybody is comfortable with what's really going on. I put a lot of effort into avoid trying to do this like a statistics class. So all these probability models are just a key on a, somebody complete the sentence.
I didn't hear you.
All these probability models that I've just shown you are simply a key on a
Calculator.
calculator. Travis got it. You probably got it a few minutes ago and I wasn't paying good attention. I'm going to turn the state of the simulation back to, there we go. Okay, so that's how it's supposed to be for prosperity. So let's now try this with some more realistic data. So I have a file here called beargrass.txt. And I'll go look at it. And what it contains is 2 columns of data. One column is a year. So 1945, 1946, up to 1975. And it has a peak value. So these are actually stream flow data for somewhere in the world. And let's load that into it and see how well a normal distribution data model explains those observations. And then we're going to estimate from our data model the value of the peak that has an exceedance probability of 0.01 or a 1% chance that we will see a value equal to or greater. In this case, we're going to use pandas because they're cute. And we will load, reason we're using pandas is because the file management's a little simplified. So we'll read the beargrass.txt file into an object named beargrass, and then we'll just look at the head, the first 5 rows of it. And sure enough, we have a column called years and a column called peaks, and they are sequentially increasing as they're supposed to. Let's do something also fun. Let me plot the values. So there's our Beargrass Creek plot. It's showing it as a continuous line, but really what you need to keep in mind is every time there's a break in slope is where there's actual and observation data. I forget what the command in Pandas plot is to make it just do markers, and I don't want to explore that right now, but there's a way to have this just do dots. So looking at that graph, let's say that's all we have to work for. If I were to ask you, what's the biggest value in the data series, what would you say?
A little over 5,000.
A little over 5,000. What's the smallest value?
Like 600.
Yeah, it's hard to say, but that's a good visual observation. What's the 50th percentile? Aha, all of a sudden that's hard because that's half above, half below. What's the mean value?
Can't really tell that here.
Yeah, can't really tell by looking, probably somewhere around 2,000. Anyway, but you do have a tool. This is a pandemonium thing. So what is the most favorite tool in pandas that Farang has taught you in lab?
Describe.
Very good. He's going to be extremely proud of you. Sure enough, there's 31 things in our series. The mean value of the year is irrelevant, but the mean value of the peak is 1,600. We were guessing around 2,000, so we weren't that bad. Standard deviation of 1,000. The smallest value was 707. We guessed 600, also not bad. The biggest value was a little bit above 5,000. We nailed that. 25th percentile, 908. 50th percentile, 1250. 75th percentile, 1945, and so on. Now at this point, let's say I wanted to know what is the value of the peak at an exceedance probability of 25%. Because that's there in the describe function, although it's not explicit.
You're asking what's the probability that it's bigger than 25, or you're asking what's the probability that it's going to be in the upper quartile, right?
What's the magnitude of a peak discharge that would be in the upper quartile?
1945.
Good. How'd you come about that? That's correct.
That's the 75% thing.
Yeah, 75% non-exceedance is 25% exceedance. And I asked the question as an exceedance type question. Now, same question, except at the 10% exceedance.
We could guess, but we can't see that using the describe function.
Yeah, it's not in the describe function. So let's go ahead and do the stuff we've already done. We'll use our already built code and then we'll modify it. Since we built it ourselves, we don't necessarily have to cite it, but we're going to employ the miracle of cut and paste. So I've already performed that miracle in advance. And so here we're going to take what we had called sample, and we're just going to take Beargrass peak, and we're going to convert it to a list, and then we're going to stuff it in a sample, and the rest of the code stays unchanged. I have played a little bit of gaming with the distribution plot to make sure that we go a little bit smaller than, a little bit bigger than the sample values. That's something you would deduce on your own after you did it otherwise to make the plots visible on both axes. And now we'll actually plot the sample. So we'll do the plotting position, but our sample is now the Beargrass peak values. And the ordering of the year doesn't matter in this particular explanation. Then we change the title, and I've introduced some weird looking strings here. Anybody know what those do?
\n starts a new line.
Yeah, it's a new line character that's interpreted by the Python interpreter as terminate the current line, start a new line, and actually it means do a line feed and then start at the beginning of the new line. And because the plotting subsystem center justifies everything, we get a pretty nice looking output. So let's run it. Oh, good, it didn't break. So there is our Beargrass Creek, and let's for this particular case, let's go ahead and say, okay, let's suppose the blue line's good enough. I mean, it's going to have to be because I've only got a couple minutes of lecture time left. Now answer the question, what is the value of the random variable at an exceedance probability of 10%? Yeah, you can actually see that in the plot. You'll have to. So where would the 10% exceedance probability value lie?
0.9 on the x-axis.
Be 0.9 here because we're plotting non-exceedance in our home built plots. We go up to the blue line, we'd read to the left, and it's somewhere between 2 and 3,000, closer to 3,000. We've already done the describe function. The 1% chance on the exceedance is the complement of the 99% non-exceedance. And so in terms of our quantile function, we want to find the value x that returns the quantile of 0.99. So rather than guessing and looking at plots, let's try to do this explicitly. Our goal is to find the 0.01, which is 0.99 non-exceedance. It's on the right side of our curve. And let's just do this by brute force. We're going to guess a value of the random variable. Then we'll print the mean and the standard deviation. That'll help guide our guess, but it's not absolutely necessary. And then we're going to print the accumulated probability based on our fitted model of our guess to 4 decimal places. And what we're trying to do is produce a result of 0.01. So let's suppose we guess 599. Now we know that that's nowhere near the 1% chance exceedance. We run the guess and it says there's a that's at 0.15. We're trying to get to what value? 0.99. So let's make it bigger. Okay, so bigger is better. We're going the right direction. We're now at 0.2. Let's make it a lot bigger. We're now at 0.58. Oh, so we finally made the median. And we would have been able to do that by guessing the mean value. So let's try mean plus 1 standard deviation, which should take us to 96%. So 1,600 plus 1,000 is close enough to 2,700 for government work. We're getting pretty close there. And let's try another standard deviation. So that would add almost another 1,000. Okay, now we're getting somewhere. What's our goal? 99. So let's try 3,900. Awful close. 3906. I think it's 3906. I'm going to go with that. So the probability of observing a peak discharge on Beargrass Creek of 3,906 or greater is 1%. The probability of observing a discharge on Beargrass Creek of 3,906 or smaller is 99%. The reason it's 99%, that's a pretty big discharge, so that's catching all the littler discharges. If we want to get fancy, we can use Newton's method, and here it's done without explanation. Newton's method is a way of taking figs and making a fine afternoon confection, and the Skippy optimized subsystem contains a method called Newton. I'll explain this a little bit. In the Newton's method is going to try to drive this function named f of x to 0. And so what f of x is essentially it's changing our my guesses until we can get the result of the norm distribution minus quantile equal to 0. So it's going to change values of x until it can get the result from the norm distribution function equal to 0.99. Then we do the subtraction. That's where we get the 0. If you want, at some point in the near future, we can do a workshop during an office hour or a pair of office hours, because it might take longer than 1 hour, and show you Newton's method done in primitive Python. On a Hewlett-Packard calculator, this is essentially the solve routine. There's a solve button that will solve functions for you. I don't know what it's called on a Texas Instruments calculator, and I have no idea whether the calculators are built in the history of the world. So if we put in our quantile value of 0.99 and we run the Newton's method, we get a value of 3902 back. So we can go into our guess and check one, and sure enough, we get a value of 99 back. Let's go ahead and put the 10th percentile in, because I think we can see that in the, let's put the 20th percentile in. We can see that directly in the plot, except I just lost my place. So 20th percentile, it looks like it's around, well, let's do the 25th percentile. That's actually in our data. If we put 0.25, what we should get back from Newton's method should be very close to 908. So let's test that. Instead, we get a runtime error. Tolerance. That's weird. It's not supposed to do that. The 75th percentile worked. 55th. Well, Newton's method's not perfect, and I'm going to just return it back to 99 and continue. So concluding this part of the example, a peak discharge of 4,000 or so would be expected to be observed with 1% chance. And keep in mind that we extracted the value from our model, not the empirical set. From a visual interpretation, for these data, our normal model is at best so-so. It's better than the flat line, but it's not comforting at this end, and it's not comforting at the low end, and it doesn't even hit the median very well. So we would be advised to look for a better model. It's okay when we're near the mean and plus or minus the standard deviation, but it's alarmingly off at either end, which is usually where our risk interests lie. So another model we can try is a log normal model. And what we do in a log normal model is we take the original data and we use a big log, and we beat the data into submission so it falls along a flat line. Just kidding. We logarithmically transform the peak values. We analyze them as if they're a normal distribution, and then we inverse transform them to recover values in the original scale. Many natural phenomena are reasonably well described by log normal. So the only difference between this set of examples and the prior one is where we applied the logit function to the list. And the logit function is a prototype function up here. And remember, the symbolic apply in pandas is a very powerful tool, and it's going to let us logarithmically transform everything in peak. And we'll call that log sample, and then we'll compute the sample mean and sample variance on log sample. We'll sort the logs in place. We'll plotting position them. We'll get the mean value, the standard deviation, and then we'll plotting position, log sample, and then our drawing of the fitted distribution. So let me run that. And it sort of looks like hitting the data with a log helped out a lot, because with the exception of these two triangles here and these three here at the right end, all the triangles touch the blue line at some point of the triangle. But now our random variable value is in log scale, and nobody often has a good feeling what a peak discharge of 6.7 is in log scale. So usually what we do is we're going to inverse transform the results back into the original arithmetic space. To do that, we're going to use our anti-logit function. And in this case, we'll do the original list. And then we'll build our distribution plot, our blue curve, except in the blue curve, when we build it, we'll use the anti-logit function so that we're no longer going to be plotting logs, although we're using the values of the logs. And if we do that, we get our plot, and there is our log normal distribution representation of Beargrass Creek. And we can interpret those in the same fashion if we're looking for mu's and sigmas. Let's go compare that to this picture. So there was our normal distribution model. So here's our log normal distribution model. Have we improved our data model? Of the two, is this a better data model for use? That's a yes. Yeah, it is. The only parts where it's uncomfortable is this leftmost observation doesn't touch the blue line, and these three don't touch the blue line. But every other triangle, for all practical purposes, there's a few in the middle that don't, more or less touch the blue line. So that's not a bad model. And like before, we can use it to predict probabilities associated with particular values. So let's try 5,000. And so the non-exceedance probability of a discharge of 5,000 or smaller in Beargrass Creek corresponds to a 99.4% chance of happening. So almost any observation you make will be 5,000 or smaller. But there is a non-zero chance of seeing something bigger than 5,000, although it's small. We want to get fancy. Let's see, I want to do a 995. We want to get fancy. We can use our Newton function. Hopefully it'll work. And the 99.5 non-exceedance, or 0.5 exceedance probability, so 0.5% is 5,020 cubic feet per second for this particular example. So now we can argue we have a decent method, and we at this point, if we wanted to distribute this code to fellow colleagues at our workplace, we would probably put everything into functions and get it to be very concise and reliable, and then do a little bit of try except so that we don't get pink screens of death when we put in unacceptable values. Another data model of interest is called the Gumbel distribution. It also goes by the name extreme value type 1. And shown here on your screen are the probability density function as a function and the cumulative distribution function as a function. And the density function has two adjustable parameters. they go by the name of alpha and beta, and has a random variable x. And similarly, our distribution function also has alpha and beta, and the this should be a this thing here, this should be a lowercase x, and it's called double exponential because you see it's the exponential of the negative of the exponential of. So the two distribution parameters alpha and beta play the same role as mean and variance. So let's modify our scripts further to see how this data model works on the Bear Creek data. So on Bear Creek, we've looked at two models so far: a normal distribution model of the data, a log normal distribution model of the data, and now we're going to look at the Gumbel distribution model of the data, or extreme value type 1. Different name, same thing. And without going into any detail whatsoever, good estimates of alpha and beta can be obtained from the sample mean and the sample variance as shown in these two formulas. Alpha is equal to mu times the square root of 6 divided by pi, and beta is well estimated by 0.45 times the standard deviation. So we will code up our double exponential distribution. Nothing unusual there. Notice I tried to adhere to the same format. Parameters go first, then the variable. And now, again, through the miracle of cut and paste, we literally put it into our prior code. So we're doing CCMR, only we're not doing one of the C's. So this is CMR. Copy, modify, run. So the changes we've made compared to our prior ones are the alpha and beta estimates, and the fitted model builds are changed right here. Everything else is essentially the same as before. The other change is we change the title. Okay, so everybody ready to see how this does? So there's our extreme value type 1. Hard to say if that's actually any better than log normal. We can still use our same guess and check approach to figure out the non-exceedance probabilities, or we could actually be really fancy. If I put a 1.0 minus, we can get the exceedance probabilities. So the probability of exceeding 3,300 is 0.009. Change that to 3,100. Let's see if I can get it to. So somewhere between 31 and 3,300 is our 1% chance exceedance. And we can get fancy by using the optimizer. And so 3269 is what it claims that 1% will be. Sure enough, that's not bad. All right, we're going to look at one last one. I'm cutting into your lab time. I apologize, but I think I'll go through it fairly rapidly. So one last model. So now our Bear Creek, we've looked at normal, log normal, Gumbel, or extreme value type 1. Let's look at another one called Pearson type 3. And this one's important because it is stipulated for use by federal agencies for probability estimation of extreme hydrologic events. And so the federal government is the same one that you and I work for in some way, shape, or form, or at least pay them money once a year, decided that the log Pearson type 3 model is the data model to use for estimating extreme hydrologic events for the, not the sole purpose, for the main purpose of issuing flood insurance policies. You can learn more at this location. This is particularly around page 276. You can also let Google do some work for us. We can look up the gamma quantile function in Skippy. And the Pearson type 3 data model looks like this. This is the probability density function. Here it is with some transformations to give it the appearance of being a 2-parameter instead of a 3-parameter model. And actually, with these transformations, it is a gamma density function. And if we read a little bit from the federal document, we can go from our sample mean, sample standard deviation, and sample skew, and make estimates of alpha, beta, and tau, all of which appear in the density function. And then we have to use the gamma CDF tool in Skippy to do the integration for us. So there's a lot going on here, but fundamentally the same as the other 3 models. So we'll have a logit function, the anti-logit function. In this case, we've now encoded our plotting position into its own function. We use Skippy Scats, Math, and NumPy. So let's load those in. And there is the gamma CDF with the 3-parameter to single parameter conversion. So that's going to handle the integration. That's going to make our blue line for us. And now, through the miracle of cut and paste and a little bit of work on estimating the different knobs in the model, we've now loaded in Beargrass Creek. We'll generate our plotting values. We'll generate our blue line, our data model. We'll do the reverse transformation of the sample and the blue line in the data model, and then we'll plot everything. So there is the log Pearson type 3. So this is the mandated distribution that would be used. And because this happens to be a flow data, regardless of any other fit that we get, we would be required on federal projects to actually use this particular distribution. It does a little bit better on the right end than any of the other 3 that we've looked at, and that's what it's designed to do. It's not so good on the left end, and that again is a known characteristic of the Pearson type 3. So let's suppose now that we're using log Pearson type 3 on the Beargrass Creek data, and we want to ask the same question. Let's find the value that returns the 99% quantile. And in this case, we'll just use Newton's method rather than guess and check. So we need some of these sample information. Basically, printed those so that I can cut those and paste them into my Newton's method f of x function. I've stipulated the value of the quantile. My guess no longer has any significance. Let's go ahead and run it. And so it claims that the 99th non-exceedance percentile is 58.56. So the 1% exceedance, the 8.9, 1% would be almost unviewable in the plot. Be somewhere up in here, somewhere between 4,000 and 6,000. So that's the visual verification. But as President Ronald Reagan once said, trust but verify. So let's go ahead and verify it. So what we'll do is we'll put this value back into our data model. So we'll logarithmic transform it, put it in a gamma cumulative density function, and see what value we get back. We're supposed to get a value of 0.990. And we get 0.9753. And that's not a surprise to me that they're a little bit off. But they're close enough at this point that with a few subtle changes and a little bit of additional trial and error, I'll just put that to 5,900. We're getting close to the value. And now let's summarize all the work that we've just done. We had 4 data models. One of the data models was named normal, one was named log normal, one was named Gumbel, one was named log Pearson 3. In our visual assessment, we would say the normal had a so-so fit, log normal was better, Gumbel was better than normal, arguably not better than log normal, and log Pearson 3 was probably the best of our visual assessment. So now in our engineering case, we would actually choose a model. Supposing we choose log Pearson 3 as our favorite, rather than just saying, well, that's what the federal government told me to use, which is an equally valid statement. We can now determine anticipated flow values for different probabilities from the data model. Our first quartile divider is 968, which represents an exceedance probability of 25%. 75% exceedance, 25% non-exceedance. Our median value, half above, half below, is 1302. Our 75th percentile, 25% exceedance, is 1860. Our 90th percentile, 10% exceedance, is 2706. Our 99th percentile, 1% exceedance, is 5856. Our 99.8 percentile, 0.002% exceedance, is 9420, and our 99.9 percentile, 0.001% exceedance, is 1145. And looking at the last three, the 5856 represents the 1 in 100 year chance event, the 9420, 1 in 500 year, and the 1145, 1 in 1,000 year. Now, clearly these last two are simply model results, because nobody keeps good enough records to know if there's been a 1,000-year event on Beargrass Creek, given that we have 33 years of observations. This last part, I think, is just extra code left behind to have available in case I broke something seriously. So the references for today's lesson in lab are our main textbook, in particular, chapter 10, sampling and empirical distributions, and chapter 15, prediction, although we have gone far beyond what these two chapters present. If you're interested more in the log Pearson type 3, this link right here will take you to bulletin 17C and has all the arithmetic that you could ever possibly want. To learn more about the gamma distribution itself, and more importantly, where I was able to find the requisite code that's presented, you could take this link. If you're somehow really interested in distributional statistics and modeling and environmental stuff, Amazon will be gladly sell you a book. Okay, I am going to turn over the class to Farhang and let him proceed with the lab. So the lab should be very much similar to what I've just presented. So I know you're all probably getting a little bit fatigued after the first hour and a half. Farhang, where'd you go? There you are.
Yes. So it is 11:40. Let's do a 5-minute break for those of you who want to get a cup of coffee or a peanut butter sandwich. I will meet you back here at 11:45. I will actually be here, so if you have a question for me, let me know.
I got the code working from yesterday.
Awesome.
Yeah.
Yay. Wow, that's a really good turnout of people, actually. They just kept coming in while I was talking, huh? Yeah, Sean has a civil engineering question. Is it? Go ahead and ask it, unless it's an advising question, then this is not the place to do it. Go ahead, Sean.
Okay, so what I see a bunch of like civil engineer people with like this tripod thing and like a hard hat on. What is that?
The tripod thing is called a theodolite, although it's actually a total station. So it's a telescope with crosshairs in it, and it's used to measure horizontal and vertical angles. The hard hats are just required because in real life they would be doing it on a construction site where people are operating heavy machinery. And the hard hat is an insurance company requirement that if you're hit in the head with a large crane, you have a hard hat on, the company doesn't have to pay your family for the headless construction worker. So that they're surveying instruments. Is that enough of an answer?
Yeah.
And what they're doing now, since they're using total stations, all they're doing is one person stands at the instrument, the one on the tripod. That used to be, that's the dumb end of the measurement because everything's robotic now. All the person has to do is put the crosshairs on the target. At the other end, person is standing with a stick. It's painted white and red, and on the stick, it has a reflector. And once they get the crosshair on it, they fire a laser beam at the reflector. It measures time of flight, so it gets a distance, and then the instrument knows what its azimuth is relative to north, so you get an angle, and you know whether the instrument is level or not, because you're supposed to level it before you start these measurements. And so that gives you the ability to measure heights above or below an arbitrary plane in space, plane, not plane that flies, but plane in space, and angles relative to a agreed upon datum, which is usually grid north. So it's actually, the instrument itself is quite complex. It has a whole lot of batteries and little widget things in it. And if you spit on it wrong, you have to send it back for calibration. But the principle is quite straightforward. You're measuring heights, angles relative to a horizontal plane, distances, and angles relative to a vertical axis. And the hard hats in case a bird poops on them. Abby, I don't know when you expire. Do you have an expiration date on your packaging?
Well, on my card it doesn't say anything, so it's like I guess it doesn't expire, or I don't know.
I don't know. I would, not to be trite, but that's a Google question. It can't be indefinite, so they're probably good for a couple years. And usually the first one is a longer training requirement, and then the refreshers are fewer. So like
It says it expires after 5 years.
I have a question when your phone.
I'm phone. Go on.
I think he means when we're done. Yeah, because D is next to F on the keyboard. Whaley, go ahead and ask your question.
Wally, is your microphone working?
Can you hear me?
Yes.
Oh, so my question is, do you guys understand how to do the international course that's required for the engineering department?
Is this a question for me or for the rest of the class?
It's for
No,
me.
for Dr. Cleaver and you.
Oh, okay.
'Cause-
Only mildly. My advice to you is going to sound kind of smart ass, but it's good advice. Contact either Allison, I can't remember her name right now. Allison Wright over in the international experience thing at the dean's office, and she can guide you to They usually do a couple of training sessions every semester that will give you some clarity in that. There's a couple different ways to satisfy it. Julissa has just said study abroad is one of them. You can also do there are faculty-led study abroads, but there's a lot fewer of those than they used to be because they're ungodly expensive. You can go to another university overseas in the summertime or do a semester abroad. And there's a few other things. If you happen to be here already on a foreign passport, you can visit with her. There's usually a workaround in those instances because technically you're already abroad. So that's the best I can give you.
Gotcha.
Okay, 11:46. Let us begin with the lab. Just before we started, you need to have your Lab 13 notebook as well as a CSV file named lab13_data.csv. You need that to be able to run the material. Okay, so I want you to refresh your non-existent short-term memories and tell me what we talked about on Tuesday. Wally, it is in the same folder as you download your regular notebooks. It's in the same directory.
We talked about populations and samples.
Very good. What is a population?
It's the set of all data.
Can you repeat that?
It's the set of all the data.
It's a set of all the data. Can I get a better definition?
Is the set where we will pull our samples from.
Okay, getting closer. What example was I talking about on Tuesday?
River flow.
Yes, the river next to my room. And in that case, what is the population?
All the possible and potential river flows of the river.
Okay. And what would be our sample?
The sample is the river flow for a specific period of time, either for a year, a specific spot, or stuff like that.
So any measurement that I make, even if it's too frequent, like every minute, or if it's not as frequent, like once a day, regardless of the frequency, those are going to be my samples. Yes? Okay. What else did we talk about?
How to extrapolate or how to take a sample from a population and how to model it and kind of predict stuff with the sample.
Yes. So something that we did talk about was how we can go from samples to population. I have another question. Why do we need to go from samples to population? Why don't we just study the population?
It's impossible to study the entire population.
Why?
You have to measure every single possible thing in that population. So you have to extrapolate from a sample.
Exactly. So because it is impossible for us to get our hands on the entire population, we use samples to infer information about the population. How many steps did we have to take to go from samples to population on a general basis?
Can you say again?
How many steps did we have to take to go from samples to population? I have one answer in the chat box from Harper. He says 4. Any other answers? Come on. It's very early in the session to be silent.
Well, they just had an hour and a half of me babbling. Harper, go ahead and state the 4 steps. Maybe that will refresh somebody else's memory and they'll think of a fifth one.
Oh man, I gotta pull those up. That was all 3 bits of my memory to remember that for.
So, if you want to try to remember what we actually did on the streamflow data, what was the very first thing that we did?
Get descriptive statistics.
Yes. So we looked at our samples and we used descriptive statistics to extract what?
Meaningful information.
Such as?
Mean, median, variance.
Very good. Thank you very much. Yes. So we looked at the data, we explored the data set, we calculated the mean, the standard deviation, and all those good stuff. Step 1, done. What did we do next? I have 46 students in the room. Come on, guys.
Sorry,
I know better than that.
I was getting the file, my bad.
Okay. So Sean says plot. Sean, unmute your mic. I remember I was talking to your head on Tuesday. Oh, your mic is not working? It's okay. I talked to your head on Tuesday. I can talk to your fingers today. So just type in your answers. So when you say plot, what did we plot? The sample. Yes, we plotted the sample on, what kind of plot was that? What were we plotting? What were we plotting? Ladies, gentlemen in the room.
I thought you were waiting for him to answer, my bad.
I actually was, but I think he's having a difficult time
Okay.
figuring the system. He's having some technical issues on his side. So, who am I talking to?
I'm Wally.
Okay, Wally, what did we plot?
We would plot the data of the sample.
We first created a plot with a bunch of points on it. Do you remember that?
Yeah, we would use the data we have and then create a plot of the sample. And then after that, we would make the model.
Yes, do not go after that yet.
Okay.
So we used our samples to create a plot with a bunch of points on it. Those points were showing us the flow rates on one side and what else on the other axis?
The peaks, or was it time?
Exceedance.
Oh, the exceedance flow.
Probability. Yes, yes. So for each one of those samples, we actually had 2 pieces of information. What was the flow rate and what was the chance or probability associated with that flow rate?
Yeah.
There is one part of that step missing. What did we use before plotting that graph?
Normal distribution?
No, normal distribution and other data models or special functions that we used came after when we wanted to plot the curve. We did something before we actually plotted those circles, and you're getting a hint in the chat box from the boss.
I was gonna say we sorted the data, but I don't know if. Oh, it is.
Yes.
Oh, yay!
Yes, we sorted the data and then we used a specific equation with ranks and length of our samples.
Ranks and lengths.
Yeah, that specific equation or formula had a name. Weibull, yes.
Oh, never mind.
Yes, Harper. That Weibull is a plotting position formula. If I scroll down on my screen, you see that we actually begin today's lab by talking about plotting positions. But before we get to this, let us finish our review. So we used Weibull plotting position. We applied it on our sorted data, and we got a graph with a bunch of points on it associated with each of our sample points. Fair enough?
Mm-hmm.
Okay. Then we said, because of two reasons, we need these points to be connected somehow. We need a continuous representation of this. Can you think of those two reasons?
Because we wanted to interpolate and extrapolate.
Thank you very much. Yes, because we wanted to have information about what is happening between those points and after those points. Exactly. So because of these two reasons, we said, we need to have a curve rather than a bunch of points. And that's where what came in?
The model.
The model. Yes, the data model, or the special functions that we talked about, or distributions. And we said that we have only one data model in the entire universe, right?
Mm-hmm.
No.
Oh, we have multiple. There's multiple types you can use.
Yes.
But it depends on what you're looking for.
Exactly. Thank you very much. So one of those that is quite common and very well known is the normal distribution model. We also have log normal. We also have these that you can see in this little figure are still some of the distributions out there. There are books this thick in multiple volumes introducing all kinds of different distributions out there. Dr. Cleveland, we couldn't hear you.
There are books that thick for just one distribution.
Yes. So just know that however we try to name them and show examples, this is in no matter all of them. We are just giving you examples of some famous ones. Okay, then we use those data models, those functions, and we draw lines. So on the same graphs that we used to have points.
That is an awesome question, John. Keep that in mind. We'll maybe get to that later. Actually, we do goodness of fit in a few lessons.
Yes.
We have a technique to help you answer that question. Good question.
So on the same graph that we used to have points, now we have lines. But how can we say whether a line is what we need to use or if it's not appropriate?
We eyeball it.
Come again?
We eyeball it.
Yes, and how do we make the judgment?
If it closely matches the points, how close it does.
Exactly. So we look at how well that line is explaining our samples. If our sample points fall closely on that line, we say, okay, this line is a good representation of these points, or this data model can represent our population well enough based on our samples. So at this point, we've managed to go from a bunch of samples to a representation of the population. Do we agree? Are we good on that?
Yes.
Okay. Okay. So that was a quick and well-needed review. Now, let's talk about plotting position. An empirical distribution based on a random sample from a possibly unknown probability distribution obtained by plotting the exceedance or cumulative probability of the sample distribution against the sample value. This fancy word is basically telling you that plotting position formulas are what you need to get a graph of exceedance probability based on your samples. Okay, exactly as we used them on Tuesday with the Weibull function. The exceedance probability for a particular sample value is a function of sample size, n, or length of our sample array, and the rank of the particular sample. When we talk about rank, you should know that we are working with the sorted sample set. Okay? So it is really important that you sort it first and then talk about rank. Otherwise, it wouldn't be meaningful. For exceedance probability, the sample values are ranked from largest to smallest. The general expression in common use for plotting position is P equals to M minus B, N plus 1 minus 2B. In this equation, M is the ordered rank of that specific sample, and N is the sample size. The value of B changes depending on what method you want to use. So when we were using Weibull, what value of B were we using? Go back and look at your lab 12. Actually, I have it right here. So Sean is saying 0. So this was the equation I gave you for Weibull. Do you remember this? So if you want to compare this with this, what value for B are we using?
There isn't a value for B.
Which means?
It's 0.
It is 0. So in the Weibull method, B is equal to 0. You can use California, you can use Hazen, you can use Cunane, and these are all different plotting position formulas, and they will give you your samples on that graph. This is the method, this is the equation that you use to get those points. This has nothing to do with your data model or your curve. Okay? Do we have any questions about this little piece of explanation that we have here on plotting position?
So for each of those methods, like all those, do they have their own purpose when we plot those?
They actually do. For
Okay.
example, in the streamflow modeling literature, it is recommended that the Cunane tends to work better for stream flows with very high variability. But something that I have personally seen, and you are going to see in this very lab, is that eventually they do not make that big of a difference.
If
Yeah,
sample
go
is
ahead.
big enough.
I mean, especially if you compare the difference between these methods and the difference that you see between data models, this is not as dramatic.
But to complete your answer, Abby, and the rest of y'all don't listen because I don't want to confuse you. Weibull, Gringorton, Cunane, Tukey, and most of the other ones are specifically optimized for a particular distribution data model. And they're not optimized for other distributions, but they're totally usable for them.
Oh, okay, thank you.
So that was a good question. Do I have any other questions on this part? Okay.
I have one question. Sorry.
Sure.
Can you tell me what M is again?
What is?
M?
M is the rank of your sample in the sorted array. So if you have 3 samples, 5, 2, and 10, the first thing that I need to do is to sort this. So it will be 2, 5, 10. And then if I'm calculating this based on, let's say, Weibull, For the first one, my m is going to be 1 divided by 3 plus 1. Why?
Because 1 is the rank.
Because
Yeah.
1 is the rank, n is the length of the total number of my samples, and then plus 1 is part of the equation. For the second one, it will be 2 divided by 3 plus 1. For the third one, it will be 3 divided by 3 plus 1, and so on.
And each of those is associated with, you had 2, 5, and 10. So that first one, the 1 divided by 3, is associated with the 2 in the sample. The 2 divided by 3 is 2 divided by 4 is associated with the 5 in the sample, and the 3 divided by 4 is associated with the 10. So there is an implicit association, but the m is simply the rank of the value of the sample within the total sample.
Any other questions?
So then what was the n again?
N is the total number of our samples. In the example that I just gave Wally, it was 3. I had 3 samples, so n is equal 3.
Oh, okay, okay.
So let the records show that with much appreciation of Abby, Sean, Wally, and Harper, I am not quite happy with the level of participation so far in this lab. Let us move on and work on our example. So, sorry, that's my dog. Someone just rang our doorbell. So let's work on the example. As I said, you have a CSV file given to you, lab13 underline data. And I hope that after Dr. Cleveland's fix, you all have access to this. We are going to first import the necessary external packages or usual suspects, NumPy, Pandas, and Matplotlib. And we are going to read this data. What do you see on my screen? Based on what you see on my screen, what can you tell me about this data set?
It's a lot of numbers compiled together.
Okay. Yeah, not the most helpful description, but that is a description nonetheless. What else can you tell me?
It's also, I guess it's a data set within rank, what we were just talking about.
Okay. How many sets do you see in this data set?
99.
You see 99 rows. How many sets do you see?
2 sets.
Yes. So we have 2 columns, we have 2 sets. Set 1, it has 100 numbers in it. Set 2, it has 100 numbers in it. Based on the first and last 5 numbers in each set, what can you give me in terms of what can I expect in each set?
Oh, based on the first few numbers?
Yes, it's like here you see the first 5 numbers in each set, and here you see the last 5 numbers in each set.
It almost looks like they're randomly generated, but obviously it's from a CSV, so you had to, write them.
First of all, how do you know that they are randomly generated? This might be my hard work for the past 5 years as a PhD student.
No, I said they look randomly generated, but I know they're not.
No, regardless of them being randomly generated or not, if you want to compare them in quantity, do you see a pattern between set 1 and set 2?
Let me give a hint. Farang is asking you to look at that picture of set 1 and set 2 and describe it without using the describe function. So set 1, what's the biggest thing you see in the picture? What's the smallest thing you see?
21.
So what can you say about the values in second one? They're somewhere between,
30 and 71. Actually, 21. and
21.
Okay.
21
the same for set two. They're somewhere between,
560 and 572 and
Awesome.
you're all getting a little too precise, somewhere between 400 and 600 in the second one. First one, what you see is somewhere between 30 and 60. So now comparing the two sets to each other, does there seem to be a ratio relationship? Is one set have values bigger than the other one?
yeah.
Would it be
Yes,
fair if we
set
say
two
that
is
set
a lot
2
bigger
is
than set
larger? Yeah,
one.
okay. Yes.
Okay.
Good.
I think we teased it out of them.
Now, we know that the data set contains two sets of values, set 1 and set 2. What is the first step that we discussed we do when we get a bunch of samples?
Do we use the
Uh,
describe function?
Yes, and what are we looking for?
the 5 summaries.
Yes, to basically get descriptive statistics of our samples and later on look at the mean, the standard deviation, and all those good numbers. So what I'm doing is that I am defining my set 1 and set 2 with the first column and the second column of my original data set. If I print it, you will see that my set 1 is here, my set 2 is here. Now, I'm going to use the beloved describe function from pandas on my set 1. Similarly, I applied it on my set 2. So here you can look at some descriptive statistics on set 1 and set 2. I'm going to give you 30 seconds, and then I want at least one of you to come out and tell me good description about set 1 and set 2. So, time's up. Do I have a volunteer?
I guess I'll go.
Okay, who was that?
Wally.
Wally, okay. So let me hear it.
So you want them in comparison of each other?
You, for now, just go in and describe the sets the way that you want. If I'm not satisfied, I'll ask questions.
Okay, so for set 1, as we know, the count is 100.
Mhm.
And then we have the percentiles, 25, the 50%, and 25%, as well as the min and max. And I guess what you could say is interesting is that every single value of set 2 is greater than every single descriptive value of set 2 is greater than set 1.
Okay, very good observation.
So I guess if someone did the math, you could potentially find, let's say, a ratio to compare set 1 and set 2.
Mm-hmm.
To say, let's say set 2 is x times greater than set 1.
Okay, thank you very much. Do I have someone else who wants to speak up? Caden, are you out there? No?
Sorry, no, I just came back. What do you
Oh,
need?
okay. So, Caden, I want you to compare the range and the IQR of set 1 and set 2, and let me know what you think about that.
The interquartile range of set 2 is 540 minus 470, so looking like 80, 70 there. And the other one is a lot smaller.
Okay, what about the range?
Same story. The range
Same story.
much larger compared to set 1.
Okay. So based on looking at these descriptive statistics, if I ask you this question, and this question is for the entire class, so please share your answers either through your mics or in the chat box. Would you say that set 2 is different from set 1?
For sure, definitely.
Yes.
Yes.
Okay.
Yeah.
Yes.
Okay. I'm waiting for any possible no's at this moment.
What do you mean different?
That is a very good question. How do we call two sets different?
Let's say two sets they have different numbers, but it's the same ratio. Let's say set 2 is this 3-time ratio of set 1. Are they the same set?
What do you think? So in my first set, I have 1, 2, 3. In my other set, I have 10, 20, 30. Do you think these two sets are different?
Yes, I think they're different. They're different numbers.
Okay. If I have 1, 2, 3, and I have 2, 3, 5, do you think they're different?
Yes.
Yes.
Where are you drawing the line?
The
When they are
ratio.
exactly the same, they will be the same. But if if one number is differing, then they're different.
Okay, so in your version, if I have 1, 2, 3, and I have 1.5, 2.5, 3.5, still you would call them different.
Yes.
Okay. John is asking a very, very interesting question. If I have 1, 2, 3 in one set, and I have 1, 3, 2 in the other set, do you still call them different?
No, I call those the same.
Why?
They have the same numbers in them.
So you do not care about the position of those numbers,
No.
but you care about their exact value.
Yes.
Okay, that's one way of looking at it. Do I have any other interpretation of the word different?
I mean, wouldn't you have to designate different sets? Like you have to say that this set is different from this set. Otherwise, they could be the part of the same set. It's just just showing different sections of that same set. You know what I'm saying?
Mm-hmm.
So it's more like a linguistic lawyer answer.
That was a good answer though. So let me ask you this. I tell you, let us Google this. How much rain? Nope. How much rainfall? 2020 Lubbock. Okay, let's say 20 inches. Let's say that Lubbock received 20 inches of rainfall in 2020. If I tell you that in 2021, Lubbock will get 21 inches of rainfall, do you think it is going to be a different year in terms of precipitation?
Can you ask the question again?
So I tell you that in 2020, Lubbock received 20 inches of rainfall in the entire year. And in 2021, Lubbock is going to receive 21 inches of rainfall in the entire year. Do you think it is going to be a different year for Lubbock in terms of precipitation? I have one answer in the chat box. Jalissa says yes. Kellen is also saying yes.
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 So do you think that managers, city managers, have to have some specific plan and to deal with this 1 inch of difference in the annual rainfall?
Yes.
I would say so.
Yes.
It's possible.
So, how many of you have been in Lubbock in 2011? How many of you were born in 2011? If I tell you that the next year, in 2021, Lubbock is about to receive 3 inches of rainfall, would you say that it is going to be a different year?
What do you mean by different year?
In
Yeah.
terms of precipitation, would you think that the same operations that you had in 2020 with 20 inches of rainfall is going to be sufficient for a year in which you are going to receive 5 inches of rainfall?
No, it's
Oh
probably
yeah,
overkill.
yes.
Jordan, come again.
I said if you're prepared for 20 inches of rain, you only get 3. That's kind of overkill, right?
Yes, and in a case like this, you're dealing with a severe drought, so you need to have a plan for that. You're going to have less water, you're going to have more dust storms, and so on. So Travis said that he has been living here his whole life, so he probably has at least a few memories of that crazy drought. 2011 was the most intense single-year drought in history of Texas. So when we talk about numbers, and in our example, sets of numbers, the difference really depends on what we are dealing with. In terms of rainfall, going from 20 inches of annual rainfall to 21 doesn't make much of a difference in any planning endeavor. If you go from 20 to 30, yes. If you go from 20 to 50, definitely yes. If you go from 20 to 2, yes. But that is about rainfall. You may be dealing with another variable that even 100 units of a change is not that big of a deal. So when we ask this question, whether set 1 is different from set 2, we have to have some sort of reference to decide on that. If it's above that, we would say yes. If it's below that, we would say no. Keep this in your minds. We are going to need this later. So we did calculate our descriptive statistics for set 1 and set 2. Do you remember the Weibull plotting position formula that we used last session? Please say
Wasn't
yes.
it like n-1 or something like that?
It was rank over n+1, yes.
Yeah.
Okay, awesome. We are going to use the same plotting position formula to plot set 1 and set 2 on the same graph. So I am defining my Weibull underline PP function, and the only argument it needs is the sample. Then it is going to create an empty list. It is going to sort those samples, and it is going to apply that equation of rank over length plus 1 on those samples and then return the values. Do I have any questions on the Weibull plotting position function? Do we all feel comfortable with it? Okay. Then I'm going to convert my set 1 and set 2 into NumPy arrays. I'm going to apply the Weibull underline PP function on both of them, and I want to plot them. So I first set the aspect ratio for my graph. I plot set 1 underline way on the x-axis, set 1, which is actually those numbers on the y-axis with the color blue. So my set 1 is going to be in blue. And then my set 2 is going to be in orange. And I set the x label, y label, and the title. And when I plot it, I get this. What is the meaning of this plot? What do you see here?
From what it shows, in terms of shape, they're similar, but in terms of value, the yellow one is massive times the blue one.
Okay, so if I ask you, what is the number associated with 60% exceedance probability in set 1, what will you tell me?
Set 1 is the blue one, right?
Yes.
Then 50.
You would say 50. How about set 2?
Set 2, 520, in that range.
Okay, so you went from 50 to 500. What about 80%?
80 for set 1 is,
Mhm.
let's just say 80 as well.
Okay.
And then for set 2 is maybe 550, 540.
Okay. So by looking at this graph, our initial estimation on the fact that set 2 is bigger than set 1 is now more strong. Do we agree? Do you see a clear difference between set 2 and set 1 on this plot?
Yes.
Okay. Now, let us move on. Did it look different? How? We talked about it. Now, we are asked to define functions for Green-Gorton, Cunane, California, and Hazen plotting position formulas. We are asked to overlay and plot them all for set 1 and set 2 on 2 different graphs. So far, what plotting position formula did we use to get this graph?
Weibull.
Now we are asked to get the same thing for Green-Gorton, Cunane, California, and Hazen. Do we have the equations for these?
Above, I think.
Yes, above in this table, you have the equations for these. So we basically CCMR ourselves. We copy the Weibull function, we paste it here, and we modify it for Green-Gorton plotting position formula. We are asking for the samples as our argument. We create an empty list. We sort our samples, and the difference from the Weibull plotting position formula comes in this line. So now we go with minus 0.44 and plus 0.112. This was different in the Weibull function, as you notice here. So we make this modification, we change the name of the function, and now we have our Green-Gorton plotting position function. We apply that on set 1 and set 2, and we name it set 1 underline grin, set 2 underline grin. The same thing for Cunane. Everything stays the same. We change the name of the function and the formula. Here we have minus 0.1, minus 0.40, and plus 0.2. We define the Cunane function. We apply it on set 1 and set 2. For the California, the equation is very simplistic. So we apply it, and then we run it on our set 1 and set 2. For Hazen, again, we change the formula. We change the name of the function, and then we apply our Hazen function on set 1 and set 2. Do we have any questions up until this point?
So right now we're just doing it. We're just taking the data sets and we're using each of the models to make a model for each one.
Yes, we basically define a function for each plotting position formula, and then we apply that function on set 1 and set 2. Good. Do we have any questions? All right.
No.
Now, as we were asked, we are going to plot them on top of each other and see how different they are. So set 1 underline way with set 1, set 1 underline grin with set 1, set 1 underline CUN with set 1, and so on. I will have 5 of them for Weibull, Green-Gorton, Cunane, California, and Hazen. And when I plot it, I'm going to get this. Do you see their difference?
Not really.
They
It's like-
they are different because you are able to see different colors up in here, especially when you go to less crowded areas like up here, but they are very close. And Abby, that is why Dr. Cleveland and I answered your question like that, because they are different, but they are not that different. So you can use them interchangeably in many cases.
I have a question.
Sure.
How did you plot on the same table again?
So here, I first set the aspect ratio of my figure. May seem that that's to answer your question as well. I'm going with a 12 for width, 8 for for height, and I simply just plot them back to back. So I'm using the dot scatter function, and I'm not doing anything specific. I just plot them.
Okay.
And if you notice, I'm using different markers to kind of show the difference here.
Wait, for your s equals 20, why is the first one s equals 50?
Because I want it to be bigger.
Oh, okay.
Yeah, that changes the size of the marker for you. Okay. Do you have any questions about plotting positions, how we calculate them, how we plot them, and how we interpret their graph? No? Okay. On the next step, we are asked to plot a histogram of set 1 with 10 bins. Do you remember histograms? When did we talk about them?
Was it lab 9?
Pretty much. I'm not sure about the number, but we talked about it when we were introducing matplotlib after NumPy and pandas. Okay, so I am setting the aspect ratio for my graph. I'm defining my set 1 again, just to be sure, and I'm using the hist function, and I'm applying that on my set 1. I don't want a grid. I want 10 bins, and I want it to be navy blue. I set the title, the X label, and the Y label, and then I want to set horizontal grid lines in yellow color. And when I plot it, I see this. I want a volunteer to come out and tell me what I can infer from this histogram.
The most amount of numbers happens on the 55 range.
Okay, Brandon, let me ask you this. What am I showing on the x-axis?
The value of the numbers.
The value of the numbers. And what am I showing on the y-axis?
The amount of them.
Which means Nathaniel, yes, that is exactly correct. So basically what we see on the y-axis is how many times I've had a number in that bin.
Oh.
Okay, so for example, I have a bin here that goes from, I guess, 10 to 20. And if you look at this, I have, it goes up to 5. So it is telling me that I have 5 numbers between 10 and 20. How many numbers do I have between 20 and 30? Let's say this is 30.
6.
So we can use this graph to infer what Brandon told us earlier. Brandon, can you repeat that for me?
The most amount of numbers counts at each value happens at on the 55.
Okay, and you because we're using bins, you want to say from, for example, 50 to 55, something like that.
Yeah, yes, sir.
Okay. And if you look in the middle, we have more numbers in the middle and less numbers in the high and low ends. So I had an interesting comment from Travis. Travis says the data is in the shape of a bell curve, or the bell curve represents a specific kind of data distribution.
Normal distribution.
Normal distribution. So is this histogram giving you a hint of a specific data model? Is it only Travis, or do we have other students who see a bell curve here?
Yeah, it looks like that to me too.
Yeah, I can see a bell curve.
Okay, so let's keep that in mind. Now we are going to plot a histogram of set 2 with 10 bins. I'm going to do the same thing, but this time I'm going with a dark orange for the color. And I will get this. What can you tell me about this histogram?
It seems to be a bell curve as well, but in the end might be an outlier.
Okay, that is one way of looking at it. If you want to tell me about where I have the most frequency of samples,
Oh,
what would you tell me?
the most frequency of samples is from 450 to 500. But I would say, let's say 480 to 510.
Okay, and does this match the observations that you made earlier when you were looking at the data set and you were exploring it?
Yes.
So if you compare the x-axis of this histogram with the x-axis of this histogram, do you see a particular difference?
Yes.
What is that difference?
Well, it's 400 to 600 on set 2, and the other one on set 1 it's 20 to 80.
Okay, and Harper says in the chat box that it is 10 times bigger, which is not a bad estimation, but we will know more about that later. Abby, could we say that it's a slightly positively skewed? I guess it is better to not pass that as a certain judgment at this point, but that is definitely something that you can keep in mind. So,
Well, also, set 1 is going up by increments of 10, while set 2 is going up by increments of 50.
okay, so even the range is bigger for set 2.
Yes.
Okay. Now, if I plot them together on the same plot, I'm using this syntax to get 2 histograms in the same panel. What do you see? Do you think this is giving you a better medium to compare set 1 and set 2?
That's a lot better, having both of them on the same graph, I think.
Okay. What do you see here? Go ahead, Abby.
You could see that in set 1, it isn't too spread out as a set 2. Even if they have the same counts, but like set 2 has higher values, so I would assume that like the values are greater, it's gonna have a wider spread, I guess. But I don't know if that's like valid.
Okay, so you have a smaller range in set 1, which coupled with the fact that their number of samples are together means it will be more squished. But for sample 2, you know that you are dealing with bigger numbers, as Harper said, almost 10 times, and you are dealing with a higher range and a wider spread that goes from 400 to close to 650. Is there anything else that you see here? Where are you standing on your bell curve theory, Travis?
Sorry, it just took me a while to figure out where the button was.
It's all right.
Stand by it, I suppose.
Do you still see bell curves?
Yes, they're just skewed.
Okay. So I want to use this opportunity to introduce you to a very cool package in Python known as the Seaborn package. If you run it like this, there's a high chance that you're going to get an error because you need to install this package. So follow me. We will just go open a new Google page and say install Seaborn. The second link that you see says pip install Seaborn PyPy. Click on it. You will see this on top of your browser, and there's a copy to clipboard next to it. Click on that. It will tell you that it's copied. Then go to the search bar of your computer, not the search bar of a browser. Go to the search bar of your computer, especially if you're on a Windows machine. If you're on a Mac machine, there is a different way that you need to follow. You want to open Anaconda prompt, which looks like this. And then you just Control V and paste pip install Seaborn in here. You hit enter and it will be installed for you. Then you will just refresh your Jupyter Lab and you will have access to Seaborn. Very similar to how you installed Pretty Table and other external packages. So what can we get from?
If it says requirement already satisfied, what does that mean?
That means that it's already installed.
Thumbs up.
Yeah.
Okay. Thank you.
So using
I just put in the chat box. Some of you may get an error. Try changing the word pip to pip3 and doing exactly what he said. But only if you get an error.
Thank you, Dr. Cleveland. Once we have Seaborn installed, we can import it, very similar to other external packages that we always import. We are going to use the distplot function from Seaborn and apply that on our set 1 and set 2, same colors. And I'm setting rug equal true, and I'm going to explain you what rugs are showing us. So getting this, it is the same histogram, but it looks a little different. First, do you see these little tiny lines at the bottom of your histograms? Please say that you do.
I do.
Yes.
Okay.
Yes.
So these are rugs. For every single data point and number that you have in your set, there's going to be one rug below that number. So you can actually see that, for example, here in the middle, you have more compacted rugs, and here at the end, where your actual samples fall within the bin. So it gives you one additional layer of information on top of your histogram that you were getting here. What else do you see in this plot that we were not seeing before?
You see the actual curve.
We see a curve. Very good. What is that curve?
The orange one is a normal distribution. While
you don't want to say that yet, but you can say that the orange one looks like a classic bell curve, so similar to what Travis said. These curves, these lines, both the blue ones and the orange ones, and this technique is known as kernel density estimation, or KDE. It is a non-parametric way to estimate the probability density function of a random variable. Kernel density estimation is a fundamental data smoothing problem where inferences about the population are made based on a finite data sample. Interesting. This sentence sounds very, very similar.
Is it extrapolation?
This is exactly what we've been doing since Tuesday. We have a bunch of finite data samples in what we are dealing with today, set 1 and set 2, in what we were talking about on Tuesday, my measurements from the river. Thank you very much. These were my finite data samples, and we are trying to make inferences about the population based on those samples. Now, in this example and in this graph, Travis, tell me whether this line helps to support your theory or not.
Sorry, the purple line or the orange line?
You can look at both of them.
Well, I suppose it does, because it's still a distribution of data over quantity, or I suppose that would be quality on the X or the Y.
Yes, man, be stronger.
Travis, just say they both look like a bell.
Yes.
You're right.
Not only they look like bells, I can hear the bells looking at them.
Yeah, which one has the lower pitch? One of them goes dum, and the other one goes ding.
The orange one would have the lower, because it has a lower.
Yeah.
See, you can hear them as well. The bells of Notre Dame.
The bells are ringing.
So, I want you to understand how useful KDE can be, because this is something that you are going to find extremely useful in your future careers. Now, here I'm using the disk plot to look at only one of the sets. This gives you a better resolution. Do you see what the rugs are doing for us? We know that, for example, we have this amount of frequency between, say, 15 to 35. But these rugs are actually showing us where those numbers fall. So, for example, around 20, it is more crowded than closer to 15. And you can see this curve, again, looks like a bell curve. Do we have any questions about histograms and the Seaborn package?
I have one quick question. Can we say to infer that we don't have outliers, or?
I would say a box plot is a more appropriate tool to pass a judgment like that, because let's have a look at this here. This is telling you that you have an observation around 700. But you cannot really be sure whether that is an outlier or not. This only tells you that you have more numbers in between and you have less numbers in the extreme ends. But that doesn't give you much information on the presence of outliers and on the severity of them. You see what I mean?
Oh yeah, I was just curious, that's why.
Yeah, let me actually double check that with Dr. Cleveland.
I'm looking up something on outliers now.
Okay.
My current research, we use a technique called, it's either PILF or PLIF. Outlier identification is not trivial. We're not going to get to it in this class this semester. There's fairly elaborate computational schemes to identify outliers in a collection of data from a sample. Remember the Beargrass Creek example, the 3 high numbers? If we applied the PLIF scheme to it, or PILF, I forget what the acronym spelling is. That's what I was trying to look up. The last value, that one that was like 5,800, that gets identified as an outlier. The PLIF. And there's 2 kinds of outliers. There's high outliers, the right end, low outliers, the left end.
Thank you very much. So let us move on.
A classic
Now-
answer on my part.
Now it is time for us to move to data models. We have looked at our samples. We have guessed that they look like a bell curve, so they might follow a normal distribution. So let us actually go on and fit a normal distribution data model to both set 1 and set 2 and see how well they fit. So set 1, set 2, I'm defining them. I'm converting them to NumPy arrays. I'm applying the Weibull function on them. I am defining my norm dist function, which is my normal distribution data model. I'm calculating mean and a standard deviation of set 1 as mu and sigma. And then similar to what I did on Tuesday, I'm going to plot it. What do you think about this fit? Don't give me that face. This is a beautiful fit.
We can do better. That's the mood.
Okay. Do I have any other opinions on this?
Wait, you can do better than this?
Yeah, that's a
Well, that's what Abby said, but you can have your own opinion.
I would argue,
Like a better fit.
unless like you can force the beginning down a little bit, this is probably as good as you get.
I honestly like this fit. And as the person sitting in the God mode, I assure you that a normal distribution data model is the best data model for this data. And I will tell you why later at the end of the lab. So we fit a normal distribution data model based on the mean and standard deviation of our samples. We'll look at it visually, and based on how well this line falls close to these samples, we can say whether it is a good fit or not. Similar thing for set 2. What do you think about this one?
Pretty spot on.
Thank you. That's what I like to hear.
See-
It can do a little better maybe here, but for the rest of the points, it is doing pretty good. So now that we have run and applied a data model to our samples, and we said, okay, it is fair enough. It is a good representation of our population. We can actually go on and create a new set of samples based on our data model. Let me repeat that. We had a bunch of samples to begin with. We looked at them, we did some calculations, we find a data model that fits those samples pretty well. We concluded that this data model can be a good representation of our population. Then we can say, okay, since this function is describing my population pretty well, I can actually get a bunch of random samples from this, and they will be a new sample set. So based on mean and standard deviation of set 1 and set 2, I am getting 100 new samples out of my data models. So this will be set 1s and set 2s because I want to keep them differently. The underlined s added to the name means that they are the artificially sampled set based on my data models. So this is my set 1s, this is my set 2s. Does this look similar?
Wait, to each other or to the original?
To the original.
Oh, yes.
Yes.
So let me actually move on and plot everything on top of each other. So blue and green are set 1s and set 1. So green is my original set 1. The blue that is falling kind of behind that is my set 1s. The red is my set 2 original, and the orange is my set 2s. Would you say that set 1 and set 1s are similar, or different?
There's
Can you repeat that?
similar.
So I have one similar from Abby. I have one similar from John G. Jordan, what do you think?
Oh, your similars are coming up big time in the chat.
Yeah, so
Right.
it's they're similar.
You got good.
Oh, really? You are the guy who said 1, 2, 3 and 2, 3, 6 are not the same.
They are
Do you-
similar, they are not the same.
Okay.
Yeah.
Yes, that was a good answer. That was a very good answer. What do you guys think about set 2 and set 2s?
They are similar.
They're
They're
not the same.
Yeah, they're similar, but you can see some slight differences.
Yeah, they're different colors for one thing.
Now, what do you think about set 1s and set 2s? Are they similar? Or are they different?
Wait,
They're
asking
different.
about-
Oh,
Set
sorry.
1s and set 2s.
To each other.
Yeah, those are different.
Good.
It's hard to tell with the blue starts and stops because the coin is kind of on top of it.
Okay. Now, we are going to use another tool that we have already discussed before, box plots. We're going to plot 4 box plots, one for each set. And by looking at this, I want you to tell me what you think about similarities and differences between 1, 2, 3, and 4. So this first box represents my set 1. The second box represents my set 1s. The third box represents my set 2. And the fourth box represents my set 2s. If you want to compare set 1 and set 1s, would you say they are similar or different?
Similar.
Why? Abby, I can't read that.
Oh no, I was using paper to compare them because it's kind of hard to
Oh,
see.
okay. Go ahead. So I want all of you in the room to share your votes in the chat box with me. Set 1 and set 2. Are they similar or are they different?
1, 2.
Okay, I have several that are saying that set 1 and set 1s are different. One of you come out and tell me, why do you see them as different? Do I have anyone in the room who says set 1 and set 1s are different?
Yes. Set 1 is blue and set 1s is green.
Any other reasons? Okay, do I have anyone in the room who would say set 2 and set 2s are different? These two boxes.
I'd say they're different.
Okay, why?
Set to us, its range is a bit smaller for one,
Okay.
and it's kind of. I'm not sure what the x-axis represents, but
The x-axis is basically the label. So this is going to be set 2, this is going to be set 2s. What you can understand and look in a box plot is the minimum values, the median, the IQR, and things like that. So now, do I have anyone in the room who would come out and say set 1 and set 2 are similar?
Absolutely not.
Very good. So, based on what we did today and using visual assessment, so we looked at cumulative distribution plots, we looked at data models, we looked at histograms, we looked at kernel density estimations, and we also looked at box plots. We realized that set 1 and set 1s look similar, set 2 and set 2s look similar, but set 1 and set 2 look different. Also, set 1s and set 2s are different. The question is, how can we know if two sets are truly, or in statistical words, significantly different or not? Caden, this is your moment of truth. You kept referring to this, that they are not significantly different. What do we mean by that? So, that's what I had for you today. And as the exercise, I've asked, what is the meaning of a statistically significant difference? Go out there, Google the question, find resources, cite them, and let me know what you think the answer is. Thank you very much for your attention. Sorry that it took a little longer than usual. And thank you, special thank you for those of you who played along with me and participated in the games. So I'm going to
Before you hand it back to me, scroll up just a touch. That is a cool to the last box plot picture.
Box plot here.
Yeah, I wanna leave you all with a thought. Scroll up a little bit more. Okay, perfect. So what I talked about lets us answer, we can answer this from these questions. If you observe a value of 425, and this is all the information you have, what's the likelihood that that value came from set 1 or set 1s? Big or small? So
Brandon says 0.
Yeah, and earlier Wally said a very small number. Correct. What's the likelihood of a value of 50 coming from set 2 or set 2s? Big or small?
Also very small.
Good. Keep that in mind, because that's going to play a big role coming up in the next few days. Now you can give me back control and I'll shut everything off.
Okay, everyone. Thank you very much for your attention.
Yeah,
Have a good weekend.
Thank you all very much. Have a great weekend. And to everyone that participated, thank you for playing along. That was a pretty good day. For those of you that just sat on the sidelines and watched, we'll get to you. So you might want to jump in. We'll see you next week. Keep in mind, you have a lot of assignments due for this class over the next 10 days. So get on them right away. Do the easy ones first and get them submitted, and then don't think about it. All right, bye-bye.
Bye, take care and be safe.